Well, welcome back, statistics scholars. Our discussion for today is probability, which much as our discussion about z-scores is a tool in your toolbox that are going to allow us to be able to calculate inferential statistics, which allows us to ask and answer cool research questions. And why probability is needed is because if you dust off your brains and remember back to our discussion of samples and populations, people who engage in data analysis, scientists, scholars, they gather samples of people, small groups of people, and then make decisions about large groups of people. And so once we start asking and answering cool research questions, like does age relate to cognitive functioning? Do men and women have different amounts of aggression? When we start asking and answering these interesting questions, our answers are always going to be based on probability because we're never going to know for sure because we don't have access to entire populations. So our discussion today is to give you a working vocabulary and a working understanding of the basic foundations of probability. Because really this is one of the important theories behind what we're eventually going to calculate as inferential statistics. So, probability is the backbone of statistics. And what do I mean by that? Well, what we're eventually going to be doing is calculating numbers for our samples that will allow us to determine how probable our data is. How probable is getting data like this? Eventually, we're going to be asking the question, something like this. If it is true that men and women have the exact same amount of aggression, how probable is it that I get a sample where men are super aggressive and women are super not aggressive? We're going to ask that probability question. But in order to do that, we have to learn the basic foundations of probability, right? So we're going to have to go over some definitions. We're going to go over some laws of probability, and we're going to learn how to solve basic probability problems so that we have a working vocabulary and a working knowledge of probability. So the first basic sort of vocab term I want you to know is the idea of an event and a trial. And it's easiest to think about probability in terms of playing cards and dice and coins. And so we'll start there, but I want you to know that everything we learn about dice and coins and playing cards can and is applied to people, right? So let's think about what is an event and what is a trial. A trial is where you engage in some sort of activity, like flipping a coin. Flipping the coin would be a trial. An event is an outcome of that trial. So if I flip a coin, that's the trial, because I'm sort of trying it out to see what's going to happen. And let's say it lands heads. Well, that's a particular outcome, and so that would be an event, the event of it landing heads. There can also be the event of it landing tails. There can also be the event of it landing on its side, although that's, not very probable, right? So you can think of an event as an outcome of some let's try it out trial. So if we flip a coin, flipping the coin as it's spinning through the air is the trial. It landing heads or tails or on its side is the outcome. That is the event. Or let's say if you have a deck of cards, you could run a trial. And you could go, okay, I'm about to reach my hand into this deck. And when you pull out the card, that's a trial. And then if you notice, and then if you go, okay, yep, that's a spade, which is one of the possible suits in cards, it's a spade, then that would be the event of it being a spade. Now let's apply this to people now. Let's say in the state of California, I'm going to use the entire state of California's population as sort of my population, and I'm about to reach in my hand to that population, and I'm about to grab someone. Me grabbing someone at random is a trial. And I might be asking, does this person have schizophrenia or not? Well, if they do, then the event is yes, they have schizophrenia. If they don't, that could also be a possible event. No, this person doesn't have schizophrenia. Or let's say you're running an experiment and you're trying to figure out whether or not a new depression drug is effective. And you're not sure if it's effective or not. And so you decide to grab a sample of people from the entire universe of all the samples you could have grabbed from a population. You grab one sample and you're like, I grabbed a sample of people and gave them all this depression drug, and I noticed that they're a whole lot less depressed than the population. I wonder how probable this is, right? I wonder how probable it is that I got a sample as extreme as this, extremely low in depression after they got the drug. Getting a very, very extreme sample, very extremely low on depression, would be an event, right? So we can explore all these particular outcomes, and probability asks, what is the probability of a particular event? What is the probability of a particular outcome? So if I flip a coin in the air, it's the trial. What is the probability of getting the event heads? If I flip a coin in the air, I might ask, what is the probability of getting the event tails? If I'm picking a card out of a deck of cards, I might ask, what is the probability of getting the event spades? Or what is the probability of getting the event hearts? Or what is the probability of getting the event six, pulling out a six? So probability always asks, what is the probability of a particular outcome, right? Or if you're applying it to people, number 3 here, what is the probability out of the entire population of California I'm going to grab someone who does in fact have schizophrenia? We can also apply this to sampling. If I have a particular population, right, there are theoretically an infinite number of samples I could grab from that population, right? Because let's say I'm sampling out of all 300 million people living in the U.S., right? The entire population of the U.S. is my population. And let's say I'm curious, right, whether or not, again, let's say I'm curious whether or not men and women have very different amounts of aggression. So I grab a sample of women and I grab a sample of men at random. And let's say someone comes up to me and says, I don't think men and women are different in depression at all. I think men and women have the exact same amount of depression. And I say, okay, well, here's 300 million people living in the U.S. I'm going to grab a sample of 100 women and 100 men, and I have these 200 people in my sample, right? But that's just one of all the 200 peoples I could have grabbed, right? I could have, instead of grabbing these unique 200 people, grabbed a different 200 people. Or I could have grabbed yet a different 200 people. There's theoretically an infinite number of people, like different combinations of 200 people that I could have grabbed, right? And so probability might ask, all right, I've grabbed this one sample of 200 people out of this 300 million. What is the probability I get a sample like this from this giant population that we'll call the parent population? It's called the parent population, and this is like my one baby sample. What is the probability of getting a sample like this? Because let's say my sample has men a whole lot more aggressive than women. In my 200 people, men are a whole lot more aggressive than women. So you might ask, well, how probable is it to get a sample of men so much more aggressive than women if in the parent population there's no difference? That's one thing probability can ask, right? But the bottom line is, for now, just wrap your head around the idea that no matter what thing you're considering, whenever you say, what is the probability of ... you're asking, what is the probability of a particular outcome? What is the probability of a particular event? And when you reach into that population and are about to grab a sample, that's the trial. And then whatever the nature of your sample is the event. And you say, what's the probability of getting a sample like this? Because you can see the outcome. You can see the event. Men a whole lot more aggressive than women in these 200 people. What is the probability of getting people like this? In the terms of coin flips, what is the probability of getting the event heads? In terms of cards, what is the probability of getting the event a red card? What is the probability in California of grabbing someone with schizophrenia? Having schizophrenia is the event. Because you're asking, what is the probability of schizophrenia? In terms of sampling, You say, I grabbed this sample where men were super aggressive and women were super not aggressive. What is the probability of getting a sample like that, where men are super aggressive and women aren't? What is the probability of getting an event like that? And this is the language of probability, where all the various outcomes are events. And so now we have to learn the formalities of probability. We always ask where probability is a number. It's a number that we calculate. And probabilities are proportions. Now, on the first exam, you might remember that I asked you to give me proportions. What is the proportion of people who would be between these various scores? Right? What is the proportion? This was the tail end of our variability lecture. And we also discussed it last time when we talked about z-scores, right? I asked you, what is the proportion of people who would be between various scores? Well, proportions are probabilities. Probabilities are essentially you quantifying how likely it is that something will occur on a range from 0 to 1, where 0 is the probability that it will never happen. And 1 is the probability that it will definitely happen, right? What is the probability that someone in this statistics class is, from the planet Uranus? Well, Uranus can't sustain human life, so that probability is 0. What is the probability that someone in this class is from the planet Earth? Well, given that everyone born thus far has been born on the planet Earth, the probability of that is 1.0. But not all events are either definitely not going to happen 0 or definitely going to happen 1. So there's a range. For example, the probability that someone in this class is going to be a woman is probably somewhere around 0.5, right? Because about half the class are women. It would be accurate to say that the proportion in the class of females is 0.51, and the probability of being a female in this class is also 0.51, right? Because about half the class. A proportion is the same thing as a probability. The amount of women in the class is the probability of being a woman in the class. And in terms of formalities, right, the closer a probability is to 0, the less likely it is that that event will occur. The closer a probability is to 1, the more likely it is that an event will occur. Here is how we symbolize probabilities. We say P, which stands for probability. And then we've put the event that we care about in the parentheses. And we call it the event, right? So the probability of event A is some number, is what I have highlighted there, right? The probability that event A will occur, where A just stands in for the event that you care about, right? And so in this example, I could say the probability of being a female in this class. The probability P of being a female in this class is 0.51. A random person gathered from this class, the probability of that will be 0.51 because that is the proportion of the class that are women. So if there were 100 people in this class, 51 of them are women. So you take 51, you divide that by 100 because there's 100 people in the class, and you end up with your proportion of 0.51. That proportion is the probability. Proportions are probabilities. If the proportion of the class that is female is 0.51, then the probability of someone in the class being a female is 0.51. It's sort of like if you know that the proportion is 0.51, that 51% of the class are women, right, females. You know that if you put a big bag of people, right, and you reached in and you grabbed one, the probability that you were going to grab a random woman would be 0.51 because that's the proportion of the class that are women. And so the way we say that in formalities here in order to calculate any basic probability, you take the number of ways for a specific event to happen. Well, if there are 100 people in class and 51 of them are women, when I reach in to my bag of people to grab someone, 51 of them are women, and so there's 51 ways for us to have the event woman. Right? So 51 goes in the top of the fraction. And then you say, okay, well, what are the number of ways for any event to happen? Well, then you say, well, I've got my bucket of people here, my big bag of people. Well, there's 100 different ways for me to pull out a person. This person, or I could pull out this person. And so there's 100 different ways for any particular event to happen, not just women, but any event. And so you take 51, the ways for that specific event, women, to happen, and you divide by the total number of possible events, right? The number of ways for any event to happen. And so when you figure out probabilities, you always have to pick the event that you care about. So in this case, I picked women. I just as easily could have picked the probability of being a male, but I picked female. I picked women in this case. And said, what's the probability of someone in this class is going to be, female or a woman? And so because I knew that there was 51 women, I said, well, 51 out of 100. Those are the most basic probability that you can do. And so let's apply this. Let's apply this to something like candy, right? I've got a small bag of candy. A small bag of M&Ms, and 6 of them are blue, and 8 of them are orange, and 10 of them are brown, and I'm going to draw an M&M out of this bag, right? Got this bag. It's a little teeny bag. And I'm about to engage in a trial, and I want to know what is the probability of pulling out a brown one. So I've picked brown as my event under consideration, and I'm then going to consider pulling out a brown one a success. Because that's the thing I'm considering the probability of, right? What is the probability of pulling out a brown candy? In probability, you always have to pick the event that you're trying to consider right now. Right now, we're considering the event of picking out a brown one, right? And so I'm like, okay, I'm about to do my trial. I'm about to pick out a brown candy. What's the probability of picking out that brown candy? That's the event under consideration. So I'm going to call any brown ones a success. And so I go, okay, well, what are the different ways for anything to happen? Well, there's 6 blue ones. That's 6 ways things could turn out. There's 8 orange ones. That's another 8 ways things could turn out, because I'm only going to pull out one candy. And there's 10 brown ones. So it's another 10 ways for things to turn out when I reach in and pull out my candy, right? So the number of ways for anything to happen is 24, because there's 24 unique candies. And so 24 ways that when I reach into the bag, I will reach out and pull out a candy. There's 24 ways for any event to happen. What are the number of ways for the event to turn out as a success and be brown? Because that's the event that I'm considering right now, right? Well, in the formalities, we would say, here's the formalities, the probability of it being brown. And in symbols, we put P, and then in parentheses, brown. The probability that it's going to be brown is the number of brown M&Ms, 10, on top of the number of all the M&Ms. So in this case, the probability, so I'm about to reach into my bag, the probability that I'm going to pull out a brown one is 0.417, because that is the proportion of the bag that is brown. And at this point, you're recognize that those examples I just gave you are to give you a sense of the basic language of probability. That we choose an event and we say, what is the probability of this specific event, right? And when we're only considering the probability of a specific event, and you know everything about all of the different possible events, figuring out probability is easy, right? If I know that there are, half the class is women, then I know the probability. It's super easy of figuring out the class as being a woman, right? But probability can get a lot more complicated than that, because we don't always consider events by themselves. We often consider multiple events at the same time. And so we also need to learn some other foundational concepts that are used when you start considering multiple events at the same time. So not just the probability of pulling out an orange one, but the probability of an orange one or a brown one, or the probability of being a woman or being a man, or the probability of being a woman and having blonde hair. In the world of probability, we often are considering multiple events together. So we have some other basic ideas that I need you to know. And here is going to be some of the things we're going to discuss. We're going to discuss what are called mutually exclusive events, collectively or mutually exhaustive events. And let me actually type that in there for you. Hold on. This word here, a synonym for it, is also collectively. Same with this. You can talk about mutually exclusive, right, or collectively exclusive, but usually it's mutually exclusive. Or you can talk about mutually or collectively exhaustive events. So keep in mind those synonyms, because both will come up. We're also going to talk about conditional and independent events, which are usually considered together. And then last, we're going to go over the laws of probability, multiplicative law and the additive law. And as you're learning these, and it feels really formal and super dry, and you're like, oh my goodness, when am I ever going to apply this to data analysis? I can only assure you that memorizing and really wrapping your head around these basics are going to make future topics a lot easier to understand, because these concepts, we're going to start using them when we eventually get to inferential testing, where we ask and answer interesting questions. And so learn them now as tools for your toolbox, even if they feel kind of separate from the world of data analysis. In reality, they're intimately tied. So, what are mutually or collectively exclusive events? Mutually exclusive is the term that gets used most of all, but again, a synonym for mutual is collective. Mutually exclusive events is the idea that when you consider two events together, so the probability of event A and the probability of event B, if one of the events happens, right, like you've conducted your trial and one event actually happened, like then the other event can't possibly occur. It's almost as if, and where this phrase comes from, is when you consider the two events mutually, when one occurs, it excludes the possibility from the other occurring, right? And so this is one question you might ask about two events, right? One question you might ask is, well, are these mutually exclusive events? If one occurs, will the other definitely occur? Or definitely not occur, rather, right? And so let me give you some examples, and I think this makes it a little more clear. The probability of being male is mutually exclusive, right? That event, turning out male, is mutually exclusive of being female. Now, I should mention at this point, if I was a sociologist, I might argue, gender exists on a spectrum, and being male versus female is not the same thing as being a woman versus a man, and maybe there's some spectrum of gender. But as you'll recall, when we talked about this in measurement, that's not typically how we think of male versus female. This is not typically how we think about man versus woman. The way we normally think about them in research situations is we make people pick. Are you a man or are you a woman? And you can argue sociologically that maybe that's not a thing we should be doing. But at the end of the day, that's in fact, as a society, what we do. And so how society typically treats male versus female is, if you are a male, that mutually excludes the idea that you could also be female. That's normally how we treat it. Whether or not you think that's appropriate, that's certainly how we measure things in research situations. If you check the male box, well, then the researcher is probably not going to want you to also check the female box. They are mutually exclusive, at least in today's society. Or how about this? One that's a little less controversial. If you answer 4 to a question, when I say to you, how many caffeinated beverages did you drink today? That mutually excludes you also telling me 5, right? Telling me 4 mutually excludes any other possible numerical answer, right? Or if I ask you, let's come up with a different one. Let's say I say, what color car do you drive? And you say green. And I say, is your whole car green? And you're all, yep, my whole car is green. Well, then that mutually excludes the answer of red, right? Or if I say, how many children do you have? And you say, I have 2 children. Well, that mutually excludes you telling me that you have 1. The event of having 2 children is mutually exclusive of the event of having 1 child, right? Or let's say we're talking about, football, and people are considering a particular play, and the refs have to decide whether or not the pass was caught, whether or not the pass was fumbled, or the pass was intercepted, right? Let's say I'm the player. Either I caught the pass successfully, I fumbled the pass unsuccessfully, or someone intercepted it. I can't have caught the pass successfully and had someone else intercept it. Those things are mutually exclusive, right? I can't have caught the pass and fumbled it, right? It's either I've successfully caught it or I fumbled it. They're mutually exclusive, right? Or if I ask you what kind of car do you drive and you tell me I drive a Subaru, well, that's mutually exclusive of that car also being a Chevy, right? Unless you've got some Frankenstein car. They're mutually exclusive events. And usually, to apply this to the world of variables and data analysis, the different events on a single variable are mutually exclusive. Usually you are permitted to give one answer, right? It's unusual to be asked a question and be asked, check all that apply. Normally, you're asked to choose one answer. And once you've chosen that answer, that mutually excludes you choosing something else. So they are mutually exclusive, right? Like taking 5 minutes to get ready instead of 10 minutes or 1 minute or 3 minutes. If you took 5 minutes to get ready, that mutually excludes you from having taken 10. Answering once, one answer excludes any other answers. But not all events are mutually exclusive, right? Go down here. Not all events are mutually exclusive. Some events are non-mutually exclusive. And going into the subject matter of variables, often the events of different variables, right, are not mutually exclusive, right? You've got the variable of gender, man, woman, and declined to state or other, right? And the event of being a blonde are not mutually exclusive. You can be a man and you can be a blonde. You can be a woman and you can be a blonde. You can be a woman and not be blonde. But notice how these are 2 different variables. There's the variable of gender with all its various outcomes or events. And then there is the variable hair color with all its various outcomes and events. And they are not mutually exclusive. And so most of the time, the events on different variables are not mutually exclusive, right? That's the idea. Liking pizza and liking chocolate, 2 different events, not mutually exclusive. But again, notice they're 2 different variables. Taking 5 minutes to get ready for work and then taking 30 minutes to drive to work, 2 different variables, not mutually exclusive, right? So for the most part, the events on a single variable what is your gender? What is your biological sex? The events on that single variable are often mutually exclusive. How many cups of coffee did you drink today? The various possible answers are mutually exclusive. And generally speaking, although this is not 100%, the events on different variables are not mutually exclusive. But at the end of the day, this concept of mutual exclusivity is a question you can ask about 2 different events that may or may not occur together. When the events are said to be mutually exclusive, that means if one event occurs, the other cannot. If they're not mutually exclusive, if one event occurs, the other event can. Mutually or collectively exhaustive events, now again, mutually and collectively are synonyms for the same idea. Mutually or collectively exhaustive events, this is a different question that you can ask about events, right? It's independent of the idea of mutual exclusivity. It's just a different question you can ask, right? You've got these two events that you're considering, 2 different possible outcomes, right? They may be on the same variable, they may be on different variables. But bottom line is you're thinking about these 2 different outcomes, right? One question you can ask is, oh, well, are these events mutually exclusive? If one events, the other cannot. If one event happens, the other event cannot. But a second question you can ask about events is, Or are these all the possible options? And that idea is collective exhaustion, right? Collectively exhausted. Are these events exhaustive? Have you exhausted all the possibilities when you put these events forward as possibilities? And so essentially what to be collectively exhaustive means is that you have exhausted all the possible options on a particular variable. And so collectively exhaustive events are essentially when you're considering the outcomes on a single variable, the events on one variable. And to say that they are collectively exhaustive is to say there is no other option on this variable. I've covered them all, right? So let me give you some examples of some collectively exhaustive events. Passing a test and failing a test. Are there any other options? Being single, dating, engaged, married, separated, divorced, or widowed. And I don't know, why don't I go ahead and add a new option? It's complicated. Now have I covered all the possible options? I think so. You're either single, dating, engaged, married, separated, divorced, or widowed, or it's complicated, right? To borrow from Facebook. The bottom line is, when you say that events are collectively exhaustive, you're arguing that there is no other option. And I would argue that single, dating, engaged, married, separated, divorced, widowed, or it's complicated probably cover all of the different options. Or how about this one? Being over 6 foot, being under 5 foot, or somewhere in between, right? That is covering all your bases. Examples of non-collectively exhaustive events might be this, right? Is a rainy day versus a sunny day. Two different events on one variable. What's the weather like? But there are other options. It could be cloudy, could be foggy, could be, right? Could be snowy if you're up at Big Bear, right? Non-collectively exhaustive. There are other options I can think of. Being blonde or brunette, there are other options. You can have red hair, you can have dirty blonde hair, you can have pink hair, blue hair, green hair, or rainbow colored hair. Ombre hair, which is with different colors, different shades in your hair. It's not collectively exhaustive to say, are you a blonde or brunette? Reaction times, faster than 1 second versus longer than 3 seconds. There's other options somewhere in the middle. But notice how the idea of collective exhaustion, to be collectively exhaustive, is just a formal term that means I'm thinking about a single variable. Have I covered all my bases? Have I given people all the possible options? Have I all the possible events that could possibly be an outcome on this variable? And that's the idea behind collectively exhaustion. When you're thinking about probability, you're thinking about all the different probabilities of all the different events. Essentially, you've covered all of your bases. You have thought about all the possible ways for things to turn out. That is collective exhaustion. And it's independent of mutual exclusivity, right? It's completely independent of mutual exclusivity. You can have events that are collectively exhaustive and also mutually exclusive. You can have things that are collectively exhaustive and not mutually exclusive. For example, passing a test and failing a test is collectively exhaustive and also mutually exclusive. You can't pass and fail at the same time. That is not a thing, right? Now, being single, dating, engaged, married, separated, divorced, or widowed, one might argue that that is collectively exhaustive, but not necessarily mutually exclusive. You can be married and also dating. Maybe not ethically, but you could certainly be doing it, right? And that's the idea. You can have events that are mutually exclusive and collectively exhaustive. You can have things that are mutually exclusive and not collectively exhaustive, and vice versa. These are just two different questions you can ask about events. Are they mutually exclusive? When one event happens, the other cannot. And are they collectively exhaustive? There is no other option when I'm considering this. Now, Now I want to introduce a concept called conditional probability. And this is another thing to think about, another way to wrap your head around probability, where you're thinking about more than one event. But it's a very different way of thinking about more than one event than we've been talking about so far. Because the idea of mutually exclusivity or collectively exhaustive, you're not asking what is the probability of a particular event when you ask those questions. Really, you got two events and you're going, oh, I wonder if these events are mutually exclusive. I wonder if these events are collectively exhaustive. But a conditional probability is different. A conditional probability wants to know the probability of a particular event. And again, in formalities, P stands for probability. What is the probability of a particular event? Well, you're actually going to need to figure it out. And so P, what is the probability of a particular event? Let's call it event A. Could be what's the probability of being a woman? What's the probability of being a man? Could be what's the probability of pulling out an orange M&M, whatever it is, right? But what a conditional probability does is says, what's the probability of event A given that some other event has already happened? It's like you're putting a condition on the world. That is a conditional probability. You're putting a condition on the world. You're saying, you're asking the same probabilistic question. What is the probability that a particular event happened given that some other event has already happened? That's the idea. And so let me give you an example. I might say, what is the probability of being a woman? Right? And you might say, well, we already figured this out. It's 0.51. But then I put a condition on it. I then say, what is the probability of being a woman given the person I'm considering is wearing a skirt? Oh, well, that's a very different probability altogether, right? Because you're putting a condition on it. You're saying, assume that the only people you are considering are people wearing skirts. People wearing plaid skirts or red skirts, who cares? But I'm putting a condition on it. You're only allowed to think about people who are wearing skirts. Now figure out the probability of being a woman. You're putting a condition on the probability. And that's a very different probability, right? Because what you're doing is saying you're only allowed to consider event B's. And in this example, I'm calling wearing a skirt event B, right? And so the conditional probability says, before you figure out the probability of A, in this example, the probability of being a woman, first assume that this other event has already occurred. For example, assume the person in front of you is wearing a skirt. All right? And the way you figure that out is, instead of putting all the people, let's say in a particular group of people in the bottom part of the fraction, you only put skirt wearers in the bottom part of the fraction. So you count the number of people wearing skirts. All the different ways for B to actually happen are all the people wearing skirts. One person wearing a skirt, two people wearing a skirt. Okay, let's say there are 10 people wearing a skirt. Okay, and you bring them over and you go, okay. Then you say, how many of these skirt wearers are women? And what you might notice is that all 10 are women, modern culture being what it is, right? So a conditional probability is very different. Let me show you the difference. So let's say you have a class with 100 people. So n equals 100, right? and you are interested in the probability of someone being a woman, and you know, and we'll call this baby n because it's for a smaller subset, right? And you know that 51 of these people are women, right? And so to figure out just the probability of A, the probability of being a woman, you would just do 51 out of 100 and get 0.51, right? So if the total number of people in the class is 100 and 51 of them are women, we'll call that baby n because it's a subset of that larger n, larger total number of people, you would say, and you're calling the event of being a woman A. Well, the probability of A, P of being a woman, the probability of A is just 51 out of 100. But a conditional probability says not so fast, not so fast. I'm putting a condition on this probability. Of these 100 people, I want you to only grab the people wearing skirts. Oh, only the people wearing skirts? Yep. Anyone not wearing a skirt, you got to tell them to leave the room. Okay, only the people wearing skirts. So we'll call the number of women N1 for that subset of people. But let's say another subset of people are the people wearing skirts. And let's say only 5 people are wearing skirts. Well, wearing skirts is the event B. So to figure out this conditional probability, you're only allowed to consider these people. Okay. And then you say, well, what is the probability of wearing a skirt, assuming you're only looking at the 5 people wearing skirts, assuming that you're only considering you're assuming event B has happened. The person in front of you is definitely wearing a skirt. And you're like, well, of those, all 5 of them are women. So the probability would be 5 over 5. 5 over 5 is 'So they would say the P is 1. Perfectly probable. 100% of those skirt wearers are women. And that's the idea behind a conditional probability. Put a condition on it. You're figuring out the probability of A, in this case being a woman, assuming some other event has already occurred, like the person is wearing a skirt. Now, let me give you another example. Let's say the probability that I want to eat ice cream is some certain number, right? Let's say and we'll call probability of I want ice cream A, probability of A. We're just going to call wanting ice cream, that event. I decided I want to eat ice cream, we'll call that event A, right? And so let's say the probability that I want ice cream on any particular day is 100 out of 365, right? Because 100 days out of all 365 days of the year is that would be the probability I want ice cream, right? 100 days out of all the days of the year, 365 days of the year, I want ice cream. So that would be that general probability that I want ice cream. The probability that I want ice cream, the probability of A is 100 over 365, which is, let's figure that out. .27 if I round. So the probability that I want ice cream on any given day is 0.27. 100 days I wanted ice cream. That's the event. 365, right? That's the probability that I want ice cream. But now I'm going to put a condition on it. I'm going to say, no. Not just the probability you want ice cream, period. But I want to know the probability you want ice cream given that the day is a hot one. And let's say, hypothetically speaking, I live in a place where there are only 50 hot days. That is not reasonable that's not reasonable in the valley, but that's okay, right? Let's say I live somewhere where only 50 out of the days are hot, right? So it's a very different probability to say what is the probability you want ice cream given that it's hot out. Because instead of looking at all 365 days, you only look at those 50 hot days and count up the number of times I want ice cream on those 50 hot days. And what you notice is on a hot day, of which there's 50, I want ice cream 45 of them. So the probability I want ice cream, the probability of event A, given that it is in fact a hot day, that's the event B, right? It's definitely occurred. It's definitely hot out. I'm only considering the 50 hot days. Well, that probability is 0.9 because in 90% or a proportion of 0.90, 90% of those days I want to eat ice cream. And that is a conditional probability. Now, why are conditional probabilities useful? Well, conditional probabilities allow us to determine whether or not different events are what are called independent versus dependent. Some events are completely independent of one another. If one happens, it's not going to impact the probability of the other happening at all. These are called completely independent events. It's essentially where I tell you that one event has happened, and then I say, does this alter the probability of that other event? If they're independent, then you would say no. Event A happening gives you no information about event B happening. And again, A and B are just labels. You could put any possible event here, right? Some events are what are called independent. But other events are what are called dependent. Their probabilities seem to be tied together in some way. Like when one event does happen, this alters the probability of the other. So if I tell you event A has happened, or if I tell you event B has happened, that gives you some information about the likelihood of the other event. And so independent events don't impact each other in any way. Dependent events seem to be tied together in some way in the world. And so conditional probabilities help us wrap our head around whether or not events are independent versus what's called dependent. And let's go through some examples because I think it'll make it a little more clear, right? Essentially, a conditional probability says, well, assume this one event has occurred and figure out how probable it is. It will be true that if the events are independent, the general probability, when you consider the probability by itself, if it is equal to the conditional probability, what is the probability of event A if another event has happened? If those two probabilities are the same, then what you say is, probabilistically, these events are totally independent. They don't seem to influence each other. They don't appear to be tied in any meaningful conceptual way in the world, right? However, if these two values are not equal, then we'll say that the events are dependent, that they're probabilistically dependent on one another. They appear to be influencing each other probabilistically in the real world. And so that's why conditional probabilities are useful. You can calculate the basic probability, compare it to the conditional probability. If they're the same, you say they're independent events, unrelated to one another. If they're different, though, you're saying these events appear to influence each other. They alter each other's probabilities, and you call them dependent. So let me give you an example of an independent event, right? Now, in the United States, whether or not you own a car, right, is probably not related to your gender at all, right? The same numbers of women own cars as men own cars. And so we might say that the probability that someone is going to own a car is completely independent of whether or not that person is a woman. And so we would probably say that owning a car, that event, is independent of the event of the person being a woman. Because if I look but here's how I could actually figure that out using probabilities. So let's say I look at the 150 million women living in the U.S. and I say and then I say, okay, there's a certain number of women. And then I say, okay, there's also a certain number of car owners, right? And so I look at all the car owners and I compare them to all the people that don't own a car. I go, okay, let's think about these people. And I go, the probability that someone is going to own a car, the probability that any person at all, male, female, other, Sesame Street monster, the probability that any person is going to own a car is 0.85. 85% of the people own cars. There's a proportion of adults in America who own cars is 0.85. Not everybody, but a lot of people. Most people in the United States own cars. The probability of someone owning a car, period, is 0.85. You took all the people in the United States, that would be in the bottom part of the fraction, looked at all the people driving cars in the top part of the fraction, divide, and you got 0.85. 85% of the people in the U.S. own cars. But then you put a condition on it. You say, I don't want to just look at all the people, not all the people. Any person who does not self-identify as a woman has got to leave this room. I'm not going to think about those people at all. Rather, I am only going to think about the people who are women and then figure out who owns a car. And if the proportion of women who own cars is exactly the same as just the general proportion of people who own cars, then you say owning a car and being a woman are totally independent. If I tell you this person is a woman, doesn't change the probability of car ownership because the exact same number of women own cars as just people in general. These are independent events. Owning a car and being a woman, totally independent. Knowing the person's a woman does not increase or decrease the probability of owning a car because in formal symbology, the probability of being a woman, event A, the probability of owning a car, scratch that, rewind. The probability of owning a car, event A, given that the person is a woman, is exactly the same as just the general probability of owning a car. Being a woman did not increase or decrease the probability of car ownership. And so these are totally independent events, conceptually unrelated. Gender has no effect on car ownership. At least being a woman doesn't, right? But let me give you another example with these same two variables, car ownership and gender. Let's say instead of being in the United States, we're in the country of Saudi Arabia. And you may not know this, but it's actually very difficult for a woman in Saudi Arabia to drive a car. There's been a few changes in recent, actually just months, in very recent times where car ownership got a little bit, or car driving got a little bit easier for women, but it's very difficult for women to drive a car. They're not permitted to drive a car alone. And there can be serious legal repercussions for a woman if she drives a car. And so car ownership among women is very low in Saudi Arabia. And so let's say I tell you that in Saudi Arabia, Car ownership is at about 70%. A little less than the United States, but let's say just general car ownership, about 70% of the people own cars. But then I tell you, now I'm only considering the women who live in Saudi Arabia. I'm not considering any male car owners at all. Well, that's a very different idea, right? So now I'm only looking at the women, and I tell you that among the women, car ownership is at only 0.15. So only 15%, or a proportion of 0.15 of the women, are driving cars or owning cars. Knowing that the person was a woman, knowing that that event had happened, again, conditional probability, decreased the probability of car ownership, at least in Saudi Arabia. So we would say these are dependent events, at least in Saudi Arabia, because the probability of general car ownership was much higher than the probability of car ownership if you assume that being a woman has happened, that you're only considering women. Let me give you another example from ice cream, right? Let's say that the probability that I will want to eat ice cream on any given day is 0.62. Again, that means I've taken all the days of the year, 365 days of the year, and considered how many of them I want ice cream. And let's say the probability is 0.62. On 62% of the days I want to eat ice cream, a proportion of 0.62. But then I tell you that it's hot out. Well, that's good. And I see that the probability that it's hot out, well, that's increasing the likelihood that I want ice cream. Of the hot days, 91%, or a proportion of 0.91, I want to eat ice cream. Well, now I say that my desire for ice cream, the event of me wanting ice cream, is dependent on whether or not it's hot out. It being hot out increases the likelihood that I'm going to want to eat ice cream. So these events are dependent. And so let's do a different one, right? And because I also want to point out to you this idea. And so conditional probabilities are how we can figure out whether or not events are independent or dependent, right? Powerful tool. If the probability of A is not the same thing as the probability of A given B, then the probability of A is dependent on whether or not B happens. B is influencing A, like car ownership in Saudi Arabia. The probability of owning a car is not the same thing as the probability of owning a car given that you're a woman in Saudi Arabia. Or in my previous example here, the probability that I want ice cream, period, on any given day, cold, rainy, snowy, windy, Santa Ana condition, is 0.62. But the probability that I want ice cream on a hot day, definitely a hot day, it's a conditional probability, is much higher, 0.91. So these are dependent events, right? But I want to caution you that the probability of B given A is not the same thing as the probability of A given B. You can't just flip them back and forth, right? And so here's an example. The probability of rain, assuming it's January, is not the same thing as the probability that it's January if I tell you that it's raining. Because essentially, what the conditional probability does is determine who your group is. And so what does that mean? That means if I want to know the probability that it's raining, well, I want to know the probability that it's raining today, assuming that it's already January, the only days I'm allowed to consider are the days in January, like the 30 some odd days that are in January. Any days in February, March, April, May, June, July, August, all those days, I'm not allowed to look at those days. And then I count up the number of rainy days only in January. That's going to give me some probability. But if I ask a different question, what is the probability of it being January if I assume that it's raining? Well, I'm going to be considering every rainy day throughout the entire year. Rainy days in February and March and April and all the rainy days of the year. And then when I only have those rainy days, then I count up how many of them were in January. So in both cases, we're looking at rainy days in January. But in the first example, I'm only looking in January. And in the second example, I'm only looking at all the rainy days. So that's one example. So I just want to caution you. The probability of B given A is not the same thing as the probability of A given B. Let me give you another example of why these are not the same probabilities. And you have to be real careful about which one you're thinking about. Let's say I tell you that the probability of someone being a woman, if I tell you the person is wearing a skirt or some sort of skirt-like garment, is 0.97. Well, that means, who have I told to leave the room? Anyone not wearing a skirt. I'm only allowed to look at skirt wearers, right? And almost all of them are, in fact, girls. Let's say this is an elementary school, right? Maybe there's one kid who's wearing a kilt, and we'll call that a skirt and offend the Scots, right? But the bottom line is, I'm only looking at people wearing skirts, right? Only looking and then counting up how many of them are girls. But in this other example, I want to know the probability that someone is wearing a skirt if I assume that they're a girl. Well, now I've told the boys to leave the room, and now who I have in front of me is a bunch of girls. And not all of them are wearing skirts, right? And so maybe only half of them are wearing skirts, or 60%. And so you're starting out with a different group of people. Here, you're starting out with skirt wearers. Here, you're starting out only with the girls. And so you end up with very different probabilities. Just something I wanted to caution you, that when you figure out a conditional probability, the probability of A given B and the probability of B given A, in this example, the probability of being a girl, if I assume the person is wearing a skirt, is not the same thing as the probability of asking, what's the probability of skirt wearing, if I assume first that the person is a girl. They're different probabilities. Just a word of caution. Now, so now we've got some basics under our belt. We've gotten the idea of, what is how do I figure out just a general probability? In the formalities, P is the probability, and then we say of a particular event. We've thought about, are these events mutually exclusive? We've thought about, are these events collectively exhaustive? Then we've learned about the importance of conditional probabilities, right? That you can actually use conditional probabilities, figure out the probability of event A, if you assume some other event has already occurred, right? And we can use that to test to see if different events are independent, don't influence each other, or they're dependent. They do influence each other, right? But now I want to cover some laws of probability. And these are, again, are just different questions you can ask yourself and different ways of figuring out more complicated sets of events. And the first one I want to teach you about is called the multiplicative law. The multiplicative law of probability, where you figure out what's called the joint probability, where you ask what's called an AND question. This is where you're asking, what is the probability of these two events happening at the same time? Event A happens and event B happens at the same time. I call this an AND question, and it's called the joint probability, because you're asking, what's the probability of these two events occurring? And here are the formal symbols. What is the probability of event A happening and the probability of event B happening at the same time? Well, we can figure this out for independent events only. You can't figure it out for dependent events, at least not in this class. But if the events are independent, right, they don't influence each other probabilistically, then you can use what's called the multiplicative law to figure out the probability of the events occurring together. And it's super straightforward. You simply multiply the probabilities together. So let's look at an example of that. So let's say I want to know I have a little bag of candy, and I want to know the probability of first pulling out a blue one and then pulling out an orange one. Well, as long as I put the first candy back, these two events are, that's called sampling with replacement, because you're replacing it. Then these two events are completely independent of one another. And because they're independent, you can just multiply the two probabilities together. Well, the probability of pulling out a blue one is 6 over 24, 0.25. And the probability of pulling out an orange one is 8 out of 24, or 0.33333333 forever and ever and ever, right? And so, but you're not asking what's the probability of a blue one or the probability of an orange one, but you're asking the probability of a very specific set of events. What is the probability that first I pull out a blue one, and then I pull out an orange one? It's a very specific set of events, right? And so the probability is going to be smaller, right? A specific set of events is going to be less probable than any one of the two original ones. And so you just multiply them together. As long as the events are independent, you can do this. It's called the multiplicative law. And the multiplicative law allows us to ask an and question. What is the probability of event A and event B occurring? As long as they're independent, you just multiply them together. 0.333 times 0.25 is 0.0833. And you're done. Hooray! Now again, this doesn't work if the events are not independent. And something to keep in mind, if you want events to be completely independent, you need to sample with replacement, right? And sampling with replacement works like this. Let's say I have a bag of blue and white candies. There's 15 blue ones and 12 white ones. And I want to know the probability of picking out first a blue one, the first time I grab it, and then on my second trial, pulling out a white one. Well, as long as I first put the blue candy back first, then you have a completely independent set of events, right? You're sampling with replacement, and then you can just multiply the two probabilities together, right? However, if you eat the blue candy first, well, that's going to alter the probability of that second event, right? That's going to alter the probability, right? And so you're going to have to, instead of just multiplying the two probabilities, you'll have to, where you could have done 15 over 27 times 12 over 27 to figure out the probability if you sampled with replacement. Now you're going to have to keep track of, well, now you have one fewer candy because you ate the blue one. And you'll have to multiply 15 over 27 by 12 over 26, right? And so now you've got, you have a different set of probabilities. Just the importance of sampling with replacement. And the big, and again, all you have to remember is sampling with replacement means you put the candy back first. Sampling without replacement means you eat the candy. Nom, 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 nom. Now, the multiplicative law works for any independent set of events. As long as the two events are independent, if you want to know the probability of the joint probability, event A and event B occurring, them happening at the same time, the formal symbols is P, A, and then there's this what's called the upside down U, an inverted U, B. That's the probability of event A and B. But you could ask a different question, right? You could say, what's the probability of event A or B? And as long as the events are completely mutually exclusive, remember that term from a few minutes ago? As long as the events are mutually exclusive, if one event happens, the other event can't happen, then you can just add the probabilities together because you're opening up your options now. You're saying not just, I don't want to know just the probability of event A, but I'm opening up my options now to say the probability of event A or B. And here's the formal symbols. Probability of A, U, B. The probability of event or B. One or the other occurring. And as long as the two events are mutually exclusive, then you can just add the probabilities together. Let me give you an example. What is the probability of a blue or an orange M&M? Not and, not the very specific set of events. First A happens and then B also happens, but rather you're opening up your options on a single trial, right? I want to know the probability of blue or orange. And so now you can just add the two probabilities together. Instead of multiplying 0.25 by 0.33, you're going to add them together, right, to get 0.583. And as long as they're mutually exclusive, then you can do this. Because pulling out a blue one excludes the idea that you could have pulled out an orange one on a single trial. And because a single try of pulling out an M&M from the bag. And because they're mutually exclusive, you can just add the probabilities together. Now, you can still use the additive law if you have non-mutually exclusive events. Because sometimes it's interesting to think about the probability of two events, one or the other occurring, when they're not mutually exclusive, because let's say their outcomes on two different variables, so they're not mutually exclusive. Because let's say I'm a social justice researcher, and I'm interested in this concept called privilege. There are certain people in society that may or may not have more privilege than another. Whether or not you agree with that theory or whether or not you're familiar with it is beside the point. But let's say you are, and you think that there's some privilege to being a man in the world that women do not benefit from. And let's say you also think there's some privilege to being white, to being Caucasian, that people of color don't benefit from. And you're thinking about a big corporate company, and you're interested in the probability that a person at that company is going to be a person in a position of privilege, either being male or being white. So you're interested in all the people at that company that might be benefiting from societal privilege, being male or being white. Now, you don't want just the white dudes. You're interested in all the men of color and white guys of color. But then you're also interested in all the white people, the white men of color, but also the white women, because then you've identified a group of people who have some privilege, right? But these are not mutually exclusive events. You can be a man and you can be Caucasian, right? So they don't mutually exclude each other. And so you can't just add the probabilities together, because then you end up with a probability greater than 1, and that doesn't even make sense. But you can still figure out this probability. What you can do is you can combine the multiplicative law with the additive law. You can say, well, being Caucasian and your race is totally independent of your gender, right? There aren't different amounts of men and women in different races. So these are completely independent events. So I can figure out the probability of being a man and being white, and I can actually subtract that from the probability of one or the other. Because the problem with just adding them together is that you're going to end up counting the white dudes twice. First, you're going to count the white dudes when they're male, and then you're going to count the white dudes when you count the Caucasians. Because let's say you figured out, let's say there's 100 people at this company, and let's say you figured out that 48 of them are men. There's some men of color in there, there are some white dudes in there, but bottom line is there are some white dudes in this 48. And then you count up the white folks at this company. Oops. And you say that there are 82 people in the company of the 100 are white, period. Well, there are some white dudes in the 48, and there are some white dudes in the 82. So you can't just add 48 and 82. That would make no sense. So you have to subtract out the white dudes once, so you're not counting them twice. And the way to do that then is to figure out the probability of being white and being a male by multiplying them together. Multiply 0.48 by 0.82, and you get 0.39. 0.48 times 0.82 is 0.39. And then just subtract it out once. And you add 0.48 to 0.82, and then subtract out the joint probability, 0.39. And then you have an accurate probability of the or question. The probability of being a man or being white is 0.91 at this company. 91 people out of 100 will either be white or male. So you've got some men of color in there, and you also have your white women, but you now have a group of people, 91 people out of this company of 100, or a proportion of 0.91, a probability of 0.91 are people of privilege, male or white. Now, our last topic for probability that I want you to keep as a tool in your toolbox is the recognition that everything we've talked about up to this point were things that you could count. There are 45 women. There are 51 women. There are 24 candies. There's 100 people at this company. There's, a certain number of people who are wearing skirts. Right? In all of these examples, we could actually count up the frequencies. And so we could do division We could actually figure out the fractions involved to figure out the probabilities. It's called a frequentist approach to probability, where you can actually figure out the number of events, figure out the number of women, figure out the number of men, figure out the number of people wearing cars, who own cars, figure out the number of people wearing skirts. You could count it up. But remember that not all variables work this way. Sometimes there's an infinite number of possible outcomes. Remember continuous variables, where there's theoretically an infinite number of possible events? And in psychology, we often, and in other social sciences, we often are dealing with an infinite number of possible outcomes because we have continuous or semi-continuous events. We're not dealing with discrete outcomes like gender or what experimental group you were in. Maybe you have reaction times, or there's an infinite number of possible reaction times. How are you going to figure out a probability like that? Because theoretically, if there's an infinite number of possible events, you would have like an infinity symbol in the denominator, right? Oh no, okay, so what's the probability? Let's take IQ as an example. What's the probability of having an IQ of 115? Well, that's one possible event, so I figure out the number of people with an IQ of 115, and but there's an infinite number of possible IQs. Oh, so there's infinity? So let's say there's, let's say it's 10 people with IQs of 115, but there's an infinite number of possible IQs. You may not know this, but you can't divide by infinity. Oh, okay. So how am I going to figure out a probability like this? And that is where our old friend, the probability density plot, helps us out again, right? Because instead of being able to count up the number of possible IQs, which you can't, because there's an infinite number of possible IQs, instead, we'll create a probability plot. We'll put all the possible scores along the x-axis, and then we'll figure out how probable a particular event is based on the probability plot. But unfortunately, we still can't figure out the probability of a single event using a probability plot. So instead, we figure out the probability of ranges of events using the density plot, right? And so let's look at a picture, right? Because we can't use the way we figured out probability with fractions. We can't do that frequentist approach anymore, right? We can't do ratios to figure it out. So we're going to use a probability density plot again, but even still, figuring out the probability of a single event is still problematic for us, because let's think about why. Let's ask this question. The probability of a single event where you have theoretically a continuous variable with an infinite number of possible events. And I want to know the probability, and let's use height now, right? I want to know the probability of having a height of exactly 5'3". Exactly 5'3". Well, how many possible heights are there? Well, there's theoretically, the number, there'd be the number of people with 5'3", that would be a success, because that's what I'm considering right now as a probability. So let's say there are 15 people who have heights exactly 5'3". But how many possible heights are there if it's truly continuous? Infinity. I can't, okay. So I use a probability density plot instead. And so here I have that probability plot. It turns out height is normally distributed, so I can make a pretty bell-shaped curve, right? And let's say this is 5'3". Let's say this is 5'3" right here. Right here. Right here is having the height of 5'3". Let's say that's the average, right? Well, how much space does a straight line take up? A straight line doesn't take up any space at all. So the probability so it takes up no proportion of this graph? So the probability of having a height exactly 5'3" is 0. Oh my goodness. The probability that a woman is going to have a height of exactly 5'3" is 0, because there's an infinite number of possible heights. And so the probability of any one particular height is essentially 0. But I can figure out the probability of having a height between 5'3" and 5'7". I can figure out the probability of having a height between 5'3" and 5'7". I can't figure out the probability of just 5'3". I can't, because we can't divide by infinity. And on a truly continuous variable, the probability of any single outcome is essentially 0, because you have an infinite number of scores down here. An infinite number of possible scores along the x-axis, because there's an infinite number of possible outcomes. And so the probability of any one of them is going to be essentially 0, because a straight line takes up no area on this curve. And remember, a probability is a proportion, and a straight line is no proportion of this graph. And so the probability of having any particular height is essentially 0, right? But I can figure out the probability of being between 5'3" and 5'7". I can figure out how dense that is there. And so whatever proportion is in here, whatever proportion this graph this takes up from 5'3" to 5'7", that will be the probability of having a height from 5'3" to 5'7". But you can never figure out the probability of a single event if the variable is truly continuous. And we're actually going to combine this idea with using a normal distribution to figure out the probabilities of being between various scores, and our knowledge of z-scores. We're going to combine these two things in order to figure out the probabilities in between various scores in our second lab. And so I'm going to do a short video that I want you to watch, where I explain how to do the lab, where it sort of combines this understanding that when you want to figure out probabilities on a truly continuous variable like height or reaction times or any psychological variable, which is this thing called semi-continuous, you're going to have to use these sort of probability plots. And if it's normally distributed, well, there's actually a table in the back of your book called Table A1 that allows you to figure out the probabilities between various outcomes. And we'll combine that with our understanding of z-scores. And so what I'm going to do in our next video is I'm actually going to walk you through how I solved all the different answers in the Lab 2 template. But where these concepts come from is from the lecture on z-scores and this last part of the lecture on probability, where we use probability density plots to figure out probabilities. And so do watch that lab, because it'll essentially explain how to do the lab using these concepts that we learned about in our last video and today, using density plots to figure out probabilities. All right, see you next time.